Welcome to the very first lesson in pre-calc. We are starting with chapter P. It's not chapter 1, it's the preliminary chapter. It's review. Lots and lots of review. Now, with that being said, because it's review, there are a lot of topics in each of the sections. So we're going to go through them kind of quickly. Again, because it's review, I'm not going to try and treat it like it's new and that we're just now finding out about this. This is review. We're going to treat it as such. However, with that being said, some of these topics are things that people tend to forget or possibly struggle with at times. There's a lot of notation involved, things like that. Like it's a lot of definition type stuff today. So paying attention is a good thing. There's also a few points in here that are a little bit different than things that we've learned in the past. Now, that doesn't mean that either of them are wrong. It's just little differences in notation. I'm going to definitely point that out to you. So, the very first thing that we're going to look at today is ways of representing real numbers. So real numbers, we have a lot of different types of real numbers. The first type, the most basic type, are the natural numbers. Those are also called the counting numbers. And what those are is they start with 1, and then 2, 3, 4, etc. Now, notice I use the brackets. My first bracket was not the prettiest bracket in the world, but I used these brackets. That puts these numbers in what's called roster notation. Roster notation is what we use when the numbers in there are discrete. Like we can actually list all of them. Now I didn't, I stopped with a ... but I could have kept going. You might be thinking like, well, but you can never write down all the numbers. This is true, but if I had an infinite amount of time, I could write down the infinite number of numbers. And there's nothing in between them. Like 3 and 4, there's no number that's going to go in between them that is part of this set. And so that's what allows us to use it. And again, it's called roster notation. We'll see another couple types of notation later on today. So that's the first type of number, is the natural number. The second type of number is not that much different. It's called the whole numbers. The whole numbers are all the natural numbers, but it also includes an amazing number. This number was a huge breakthrough in the idea of numbers, and that is 0. So the whole numbers are all of the natural numbers and 0. Not much difference there, but it's a little bit different. And again, writing them in roster notation. The next set of numbers are called the integers. Now the integers are defined as the whole numbers and their opposites. So we have all the whole numbers, and then we also have the negative ones. So the integers can be written, we'd have ... because it extends infinitely that way as well. -3, -2, -1, 0, 1, 2, 3, ... So it goes both directions there. So those are the integers. These number systems also have symbols that we use because mathematicians are very lazy and we don't like to write things out. Now, when I say lazy, that doesn't mean that we don't like hard work. Lazy is just an efficient way of saying efficient. So the natural numbers have a symbol, and these are all written in Blackboard bold, but it's a big capital N. And again, the Blackboard bold is where you get those two things. We'll be seeing them a lot, and I'll have them typed at some point too. The whole numbers is a W. The integers is obviously going to be a z. Why is it a z? Because I've actually heard a few different stories. I don't know if any of them are true. The one that makes the most sense is there's a German word for number that starts with a Z, and that's why they used it. But as we know, I is used for something else, so it can't be an I. The next type of numbers are the rational numbers. Now, the rational numbers are all of the integers because they're defined by any number that can be written as a fraction. Any number that can be written as a fraction. That doesn't mean it has to be written as a fraction, but it can be written as a fraction. So like 3 could be written as a fraction. That's 3 over 1. It could be 6 over 2. That's a fraction. The way that we could write this down, we would use what's called set builder notation. And set builder notation starts out with the bracket. Oh, that was a decent bracket right there. And then we have two numbers. It's a ratio. That's where rational comes from. It's a ratio. So we have a over b, and then we get a line. That line means such that, again, mathematicians are lazy. A and b are integers. And so to be integer, or for r, they're an element of, we have this cool little symbol. It looks kind of like a capital E, but it's curved and it sits like in the middle. It doesn't sit on the line. It's kind of up in the middle of the line. So A and B are elements of the integers. So we have an integer divided by another integer. And then the b can't be 0. Because when we divide by 0, bad stuff happens. When we divide by 0, that's when we get 2020. And then end the bracket. So this says all numbers, a over b, such that a and b are integers and b does not equal 0. That gives us all the rational numbers. It gives us every possible number that can be written as a fraction of integers. And the rational numbers have a symbol as well. It is obviously going to be a Q. You're thinking, well, why isn't it an R? The R is for the real numbers, right? That's what we're talking about here, real numbers. So the rational numbers is a Q, and that stands for a quotient because it's a ratio, it's a division problem. And so it's a quotient. The next set of numbers are going to be irrational numbers. Irrational numbers are all numbers that are not rational. That helps, right? So rational numbers are anything that can be written as a fraction. Things that can't be written as a fraction are going to be decimals, but not every decimal. Rational numbers have decimals that either end, also called terminate, or they repeat. Irrational numbers, they never, it's not an either, it's a both. They never end and they never repeat. Or repeat. Examples of irrational numbers, the one that people always say first is pi, because they always know it's irrational. They don't necessarily know what it means, but it's irrational. Yes, pi just keeps going forever. It never stops, never repeats. E is a much more fun and useful irrational number. That's the 2.718281828459045, blah, blah, blah. It's the natural number. We deal with it when working with logarithms and exponential growth and stuff like that. Phi is my favorite irrational number. That's the golden ratio. Other irrational numbers, though. Square root of 2 is an irrational number. Square root of 3. Square roots of integers will either be an integer, like the square root of 4 is 2, the square root of 25 is 5, or it will be irrational. So if it doesn't come out nice, it's irrational. Now again, that's of integers. A square root of a decimal could come out to be another decimal, and that's okay, because that would be the square root of a rational number, like a fraction. You take the square root of the top and the bottom, and it doesn't always follow. But the square root of an integer will either be an integer or irrational. And then, like, some people even still don't believe that, well, how could it never end or repeat? You can make an irrational number wherever you want in the number line. Let's say we want an irrational number in between 0 and 1. Well, every number in between 0 and 1 starts out with 0 point something. Well, we could go 1, 0, 1, 1, 0, 1, 1, 1, 0, etc. There's a pattern to it, yes. But does it ever end? Do I have to stop doing what I'm doing? No. Is it ever going to have to start repeating itself? No. I can keep going, adding one extra 1 on each of those. We could also go 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, I can keep going like this forever. So those are other irrational numbers. If I wanted to put them in between two other numbers, you just change what's at the beginning. Real numbers. Real numbers are all rational and irrational numbers. So it's, change my color here really quick. Real numbers are all of those and all of those. Any number that can be written as a fraction or can't be written as a fraction. Well, what else is there? We know from Algebra 2 that you also can get into imaginary numbers. The square root of -1. We're not talking about those yet. We're just talking about real numbers, because a lot of times we don't deal with imaginary numbers. Sometimes we do, but most of the time we don't. And so real numbers are very important. The symbol for real numbers is that capital R, that big blackboard bold R. There is no symbol for an irrational number, by the way. The number line. Numbers get ordered, and so we can make a number line. Yes, this is review. I understand that, but some things people don't get about number lines is that they should be consistent. The bigger ones are over here. That's something else that people struggle with sometimes, sadly. And the smaller ones are over here. A lot of times we put 0 on the number line. And so if we have 0, the bigger numbers are positive, the smaller numbers are negative. You do not always have to have 0 on the number line. If your numbers are in the 143 through 162 range, you wouldn't want to include 0, because the more important thing about a number line, I mean, there's the direction, which is hugely important, but each of your tick marks should be the same. So if this is 1, this should be 2, this should be 3. If this first one was 20, this should be 40, and this should be 60. You wouldn't want to have the first one be 146 and the second one be 147. That scale is way off. The scale has to be the same for all of these. The next piece, we have order and interval notation. Order and interval notation, I took a lot of tables from the book for actually a lot of this section, because we're going to go through it fast enough. We don't need to have each of them. But the first one, the real numbers are ordered. We have the greater than or less than symbols. This is what they mean. If A is greater than B, that means that A minus B is positive. It means that A is bigger than b. That's just a way of writing it using symbols. Um, and so we know this. The little line underneath makes it or equal to. Those are called inequalities, as opposed to the equal sign, which is called an equality. The trichotomy property. The only reason I have this is just in case for some reason you actually see the vocab word trichotomy property. Basically, if you have two numbers, one of three things has to be true. Either the first number has to be bigger than the second number number has to be bigger than the first number, or they have to be equal. There are no other options for two real numbers. That's the trichotomy principle. Bounded intervals. So this is one of those things that sometimes people struggle with a little bit. We've seen it for a few years, but still there is some struggle. And it's also something where there's a little difference here in what it says than what we've done in the past. So the first thing, we have interval notation. The interval notation is where we use these brackets. It's where we're using these guys. Now, as we can see, if we compare this row, or that column and that column, the square brackets are going to be the or equal to ones. The curved brackets, the parentheses, are going to be the ones that aren't or equal to. And we can have it where one is or equal to and one is not or equal to. That's okay. We can see what that looks like here. Now the part that's a little bit different than what we've done is in the graph. Here they used the brackets at the end of the graph, which is acceptable. We have always used dots, at least in my classes we have. The or equal to are the closed dots. The not or equal tos are the open dots, the ones where they're not filled in. And so either of these are acceptable. I made sure to keep this here so we saw it, because in your assignments and stuff, it might show it to you with the brackets instead of the dots. So you just need to be aware that that is a possibility. So that's a way of writing bounded intervals, and those are bounded on both sides. It's either equal or not equal. There's also the ones that are unbounded, where it could go off to infinity. The same thing though. The closed bracket is an or equal to. The open bracket, the parenthesis, a parenthesis is singular for parentheses. You don't get to use that word very often, so when the opportunity happens, take it. This is going to be open. Now notice that all of the infinities have open brackets, because you're never going to get there. An infinity will always have that parenthesis, never the closed square bracket. Next piece, we have some basic properties of algebra. Now, you have seen these over and over and over, and they were very possibly like common sense even the very first time you saw them. So again, I just have them copied. We're not going to necessarily take the time to write them out, but the property is the commutative property. That's the order doesn't matter. This says that 3 plus 4 is the same thing as 4 plus 3. Or multiplication. 3 times 4 is the same as 4 times 3. That's the commutative property. We can commute them. The commute is when you go to work, you move, you change your position. So we can, the commutative property means that the order doesn't matter. Notice that's for addition and multiplication. That does not include subtraction or division. Why? Because subtraction and division don't exist. They're just shortcuts. The associative property. It doesn't matter if we add the first two first and then the last one. So 3 plus 4 plus 5 is the same as 3 plus 4 plus 5. 3 plus 4 is 7, plus 5 is 12, 4 plus 5 is 9, plus 3 is 12. It doesn't matter the order that we add them in. Combine that with the commutative property, we could go 3 plus 5 is 8, plus 4 is 12. That can help us with mental math when we're dealing with big numbers that group nicely. In this case, it really doesn't matter because these numbers are all small. Same thing with multiplication. The identity properties, if you add 0 to something, 0 is the additive identity, you get the same thing. If you multiply 1 to something, 1 is the multiplicative identity, you get that same thing. The inverse property, the additive inverse is the negative, you get 0. You know, I said there's no such thing as subtraction because you're just adding the inverse. You're adding that negative number. Multiplication. If you multiply by the reciprocal is the multiplicative inverse. So here, if it was, say, 2 times 1 over 2, you'd get 1. Remember, reciprocal, if you had, say, 3 halves, the reciprocal of that would be 2/3. You'd get 1. Now notice it can't be 0 because 1 over 0 is bad news, doesn't exist, at least as you know it at the moment. And so that can't be 0 because 0 does not have a multiplicative inverse. There is no number you can multiply to 0 to get 1. And so I said division doesn't exist because you're just multiplying by its inverse. Distributive properties. Remember, when you have things multiplied, you just distribute. So that's u times v plus u times w. And then same thing, we could go backwards. So w times u, or u times w plus v times w. But the order there doesn't matter, remember, because multiplication is commutative. So we can move things around. And then distribution over subtraction, it's the same thing except you have this negative sign in there. You could change this to be plus negative w plus negative v, and you don't even need the subtraction form of this. But at some point they forgot that subtraction doesn't exist, and they showed weakness. We have properties of the additive inverse. So these are just the negative properties, basically. A negative is positive. It doesn't matter which one is negative for the second one, it'll still come out negative. So a negative times a positive in any order is a negative. A negative times a negative is a positive. Negative 1 times something is just the negative something. And then if you have a negative out on the outside, you have to distribute it to both things on the inside. So again, those are the basic properties. As I said in the very beginning of this, a lot of these are review, but there's a lot of stuff. And so it's just going and going and going, but we're trying to get through it quickly because hopefully you guys, if you didn't remember this before, hopefully you're seeing it being like, oh yeah, that's right, I remember that. Integer exponents. So these are just exponents that are just integers, so we won't have like to the 1/2 power, which you would have seen last year. You know, that's a square root, but we're not working with those quite yet. When we have an exponent with an integer, say we have 3 to the 5th. This 3 is called the base. This is called the exponent. And it's the 5th power of 3, or 3 to the 5th. And what this means is that it's 3 times 3 times 3 times 3 times 3. We've got 5 3's all multiplied together. Remember, math people are lazy, which is just efficient. This is way more efficient than writing that. So we use exponents. with exponents, we get all sorts of properties of exponents. These properties, we have little examples even that go right with them. When we multiply, we add the exponents. Because here, if we look at this, we have 5 to the third times 5 to the fourth. Well, that's 5 times 5 times 5 times 5 times 5 times 5 times 5. Is this multiplication any different than any of the others? No. And so this just gives us 5 to the seventh. Same thing when we divide. We're going to subtract because you could, if you won't think about it, you could cancel. If we had 5 times 5 times 5 over 5 times 5 times 5 times 5, we can cancel. We still have 1 on the top, 5 on the bottom, which is 5 to the negative 1, which would be the same as 5 to the 3 minus 4. Anything to the 0 is 1, because we have 0 5s. Negative exponents, just make it in the denominator. If we have two things multiplied to an exponent, we have to distribute the exponent to both things, because let's say we had 3x to the fourth. Well, that's going to be 3x times 3x times 3x times 3x, which, as we saw with the properties, the commutative property means we can rearrange them. So we can move all the 3's to the front, and then we have all the x's. Well, that's 4 3's and 4 x's. So that's the distribution. That's how it works. Now, what does not work, I'm going to change this to a bad color. What does not work, let's say we have 3 plus x to the fourth. This is 3 plus x times 3 plus x times 3 plus x times 3 plus x, which we would have to distribute. This does not equal 3 to the fourth plus x to the fourth. Very much does not equal that. You might be asking, like, wait, why is blue a bad color? Well, Arlington, duh. Let's go back to a good color. And then the last one, same thing with division. It works the same. Scientific notation. This is the last slide. Last slide is scientific notation. Scientific notation is very useful when we're dealing with very, 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 very large numbers, like astronomical numbers, number of molecule type numbers, or very, very small numbers, the size of a molecule. What scientific notation does is, let's say we have 3.6 times 10 to the fourth. The exponent on this 10, it's always a number point something. So like we could have 3.6. We would not have 0.36. That's not scientific notation. It has to be a number that's not 0, point something. Not 13.6. We would have to write that as 1.36. It's one number that's not 0, then a decimal, and then a couple numbers. We don't have too many because at some point it doesn't matter. But this 4 here, this exponent, that's how many places we're going to move the decimal point. So we have a 3, 6, and we move it 1, 2, 3, 4 places, which gives us 3 zeros. So these two numbers are the same. Why don't we use more digits? Well, let's say it was 36,005. There's a 5 in this last one. Does that 5 really make any difference in that number? No, it's a tiny little thing. It doesn't matter. It's not going to affect things. And honestly, when we're dealing with numbers that big, you have a margin of error. We don't know it that exactly, so we don't use those. We could also go the other direction. Let's say we had a really small number, like 0.0000271. Scientific notation, this is going to be 2.71 times 10 to the negative, because the decimal point got moved the other direction. So it's going to end up here. It went 1, 2, 3, 4, 5, 6 places. So we're to the negative 6. So converting to and from scientific notation can be useful, and it's something that people struggle with. I haven't quite figured out why. I think it's just because people don't think about it. They don't take it seriously enough. It's always at the very end of a long lesson, etc., etc. But we can also use scientific notation to help us do math. Let's say we had 36,000 times 45,000,000,000,000. Don't know how many zeros we have there, but that's okay. Divided by 18, we'll go 18,000. We can turn this into scientific notation. This is going to be 3.6 times 10 to the 1, 2, 3, 4, 5. Then we'll have a 4.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, divided by 18 times 10 to the 4th. Now, in scientific notation, we tend to use the little x for the multiplication. There's really no reason to do that. We could have just used parentheses here. And now, all of a sudden, we can start rearranging things. We have 3.6 times 4.5 times 10 to the, well, we just add those exponents since the bases are the same, 10 to the 14th over 18, 1.8, sorry, times 10 to the 4th. Now we can subtract these. This is going to be something times 10 to the 10th, because 14 minus 4 is going to be 10. And then 3.6 times 4.5 divided by 1.8. We can actually simplify this. Like, you don't have to multiply these things together. You can start dividing. 3.6 divided by 1.8. Well, what's 36 divided by 18? That's 2. Man, I was thinking we were going to even have to simplify those, but no, it just divided fully. 2 times 4.5 is 9. And we're in scientific notation. If, let's say, it came out to be like 12.3, we'd have to move the decimal place 1 and change our exponent, because it should 12.3 would be 1.23. But here it just came out to be 9. So perfect. So that's the topic. Again, I apologize for the length of this. There's a lot of topics to cover in these first preliminary chapter, but it should be mostly review. I say this after the fact, but maybe you watched it on slightly sped up speed since it was review, and you can always slow it down when you need to or pause it when you need to. But I won't take up any more of your time. Try the problems. I'll see you in class. Until then, keep working problems, keep asking questions, and as always, happy mathing.